Okay, well, as folks keep coming on into the WebEx, I'll just say welcome and we'll get our seminar started. So this is one of our quarterly meetings for the NASA Analogues Focus Group. And this group is sponsored by NASA SSERVI, the Solar System Exploration Research Virtual Institute. And so the goal of this focus group is to bring together folks who are interested in various aspects of terrestrial analog research. So spanning from science and technology and operations, and bring everyone together so that we can hear about what other people are doing in the field, foster collaborations, lessons learned, and bring up new opportunities and such. So thank you all for joining. I'll mention that this talk will be recorded, and NASA SSERVI will be posting it on the website. So there are some people who couldn't come today who can go and watch it later on. So before we get started with our talk today, in the spirit of fostering collaboration and bringing the analogs community together, Lauren Edgar is here and is helping sponsor an upcoming analogs workshop. So Lauren, if you want to say a few words about that, because I know the abstracts are due next week, so it's not too late for people to participate.
Yes, thank you for the reminder. I figured this would be of wide interest to this particular group. So the USGS is sponsoring a workshop on terrestrial analogs for planetary exploration. We had initially hoped to host this workshop here in Flagstaff, followed by a field trip at the end of the week, but this year everything has had to turn virtual, so it'll be a virtual workshop June 16th to 18th. And abstracts, they're just one-page abstracts, are due next Thursday, April 22nd. If you guys have any questions about it, feel free to reach out. The intent of the workshop is really, to foster these kinds of collaborations. We'll be highlighting different planetary processes, exploration strategies, orbit to ground comparisons. It's done in collaboration with the Planetary Geologic Mappers meeting because we think there's a lot of overlap with that community as well, which will be the first part of the week. So hope many of you will consider submitting abstracts, and we look forward to further discussion then.
Sounds good. And Eldar, yes, we can put the link to the workshop in the chat. That way folks can find it easily. So great. So there's a lot of activity happening in the analogs world, even in our virtual settings these days. So on that note, I'd like to welcome today's speaker. We're very fortunate that Dr. Gordon Osinski has joined us today. And you may also know him as Oz, so I think you know you've made it when you can go by one name. So Oz is a professor in the Department of Earth Sciences at the University of Western Ontario, also known as Western, in Canada. And he is the director of the Institute for Earth and Space Exploration at Western and the director of the Canadian Lunar Research Network and the founder and chair of the Planetary Sciences Division of the Geological Association of Canada. He's a member of multiple advisory committees, including the Space Advisory Board of the Government of Canada. So Oz's main research interests focus on understanding impact cratering as a planetary geological process on the Earth, Moon, and Mars. And he has been involved in many past and ongoing exploration-related activities. Just most recently, one of his activities, he's the PI for the Canadian Space Agency's concept study for an integrated vision system for the characterization of the lunar surface. He's also a co-eye on the PanCam instrument on the 2022 ExoMars mission to Mars. And Dr. Osinski is also involved in providing geology training to both Canadian and US astronauts. So Oz, we're delighted that you were able to join us today. And I will turn it over to you for your talk. We'll let Oz speak and then we can do Q&A at the end as well.
All right, well, thanks, Jen, for the introduction. It's an absolute pleasure to be here today. I recognize a lot of familiar names on in the WebEx there, so I hope you're all keeping safe and well during these kind of virtual times we're living in. So I think I'm probably preaching to the converted here, but I'm a strong advocate for analogs, and I think as we ramp up for Artemis and sending astronauts back to the moon, there's a need for even more analogs in preparation so that we really maximize the return from these future missions. As I was putting this together, I realized I have several hours to talk about. So I'm going to try and really condense this into about 45 minutes to give some time for questions at the end. But in some of these slides, I've probably put in more text than I usually would do in a presentation. So that's there as a resource, for you to go back to. Or for those, some of you watching this now might be watching it for the first time after the fact online too. So let's just jump right into it. My name is the only one on the title slide. But I have a huge number of people to thank, well over 100 people, faculty, staff, many students, undergrads, graduate students, and postdocs to thank. This is from some of our early missions starting about a decade ago. and our most recent one that I'll talk about briefly at the end, CanMoon, which was conducted 2 summers ago in 2019, right before COVID. So thanks to all of these people. It would take me the entire 45 minutes to thank you all, I think. I think I'm getting a little bit of background noise with some doors shutting, so if you can all make sure you're muted, that will save me from being distracted. Thanks. Okay, so this is most of the analog missions that we've conducted over the last decade now, going back to 2010. One of the most kind of well-documented and well-written up, I'm not going to talk about today. I'm just going to refer you quickly to a special issue published in Planetary and Space Science on the CanMars. This was focused on Mars sample return, but it's really applicable and appropriate, I think, for any robotic sample return mission. And so there's this is an overview paper that you can see on the right-hand side, and then there's about another dozen or so papers in that special issue. So today I actually wanted to go back because I think it's actually one of the most relevant as we're looking to send humans back to the moon. Some of these early missions, analog missions at the Mustaston Lake impact structure, and then hopefully at the end, I've left enough time to talk about the CanMoon analog mission to Lanzarote in Spain that we conducted most recently in 2019. So, Mustaston analog missions. This was I should have also acknowledged on the first slide, just about all of these analog missions and the results I'll be talking about have been funded one way or another through the Canadian Space Agency, so thanks to them for funding. This analog mission was carried out under contract to the CSA about a decade ago. I think they were ahead of the curve in realizing the importance of analog missions, and that was basically the title we had back then. Was lunar analog missions in support of future human sample return missions to the moon. We're maybe a bit overly optimistic, but hopefully this time around we're getting super close to seeing humans go back and robots returning samples, and of course that is already happening. So this was, I think, quite unique in that we ran this analog mission to the same place, the Mustaston crater that I'll get to in a second, over 2 years, in 2010 and 11. In year one, it was a robotic precursor scenario, and then the second year we followed that up with astronauts. And one of the key things we wanted to look at was the value of robotic precursor missions. All of these analog missions that I'm talking about here, I call them analog missions because they were full end-to-end mission simulations with a remote mission control team down here in London, and then a field team in some remote part of the world. We had established science goals, and in this case, it was impact chronology, shock processes, ejector, and resources. So Mustaston, why Mustaston? If you don't know about the Mustaston Lake impact structure, it's located in Labrador up in northern Canada. It's below the tundra, so it's not quite as high Arctic as the scene behind me on my screen, which is the Horton crater on Devon Island. Mustaston is a complex crater, relatively young geologically speaking, about 36 million years old, 28 kilometers across, so fairly sizable. But one of the two unique things about Mustaston, one, is that it's one of only 3 craters in the world that have any proportion of anorthosite in the target, and it actually has by far the greatest volume of anorthosite, so a great lunar highlands analog. And it also is well preserved. It has a series of impactites, including preserved ejector deposits. And you can see on the bottom here, there's a cliff about 5 meters high with beautiful columnar jointed melt rocks and various types of breccias. So, kind of high priority science targets that we want to find when we go to the moon. Like a lot of these analog missions we've conducted, we kind of really start at the basics. So we conducted a site selection workshop. I had actually only just visited this site for a reconnaissance the year before, but everybody, just to kind of highlight too, everybody involved in the site selection, the mission operations, had never, visited the site, and so they really had no a priori knowledge of the site. So we kind of started back then. We didn't have quite as high resolution data. We were able to get some radar sat data relatively easily from the Canadian Space Agency. So that's what you're seeing here. And we essentially conducted a workshop. We had to take various things into account, including where we could land in such a crater. But we really started with a clean slate and picking out sites of interest, which are all of these places in yellow dots. After that, it then became a look at logistics and relevance to the science objectives we have. So we actually picked out 3 main sites. There's a place called Discovery Hill that I'll show in a second, Cote Creek that I won't talk about today, and this rim site out on the right-hand side. So the first summer, we focused again, so this is back in 2010, on a robotic precursor mission. I do want to acknowledge that for various reasons, we didn't use a rover for this first analog mission. We did in the following year. So we essentially had humans as proxies for rovers, but we had quite strict controls on where people could go, so that we're not being completely sending them climbing cliffs and things, collecting samples that a rover couldn't get to. Although I acknowledge that some of these places were fairly rugged. This is the instrumentation that we had for that first analog mission. Not quite all of it, but mostly. So imaging. We had PanCam type stand-ins, LiDAR. This is you'll see this a bit 3D scene modeler. We had essentially a rover mounted in a handheld stereo camera that allowed the creation of 3D models. We then had some subsurface information from ground penetrating radar, and then a Bruker X-ray fluorescence spectrometer for providing some geochemical data. And then we also had Raman and a couple of other tools as well. And this is what it looked like. This is actually where Mustaston is. So if you kind of turn your head slightly sideways, Labrador, this is Newfoundland to get your geography. And we're located right down quite close to the US border, down in London, Ontario. For communications, we had this satellite terminal provided by MDA. This ended up being quite a significant challenge, was having enough bandwidth and communications. So this did affect quite a bit of the astronaut simulations in the following year. And that real-time comms were quite tricky, if not impossible at times. So I'm not going to kind of focus on that aspect of these analog missions. Context is critical, right? Again, I'm probably preaching to the converted here, but if you want to make the most out of samples that you collect, having as much context as you can is absolutely critical. And so this is kind of the step through of the sequence that we would use in that first robotic precursor year. And not every step on here was done at every single time. So we did come back with quite a wealth of information from that first summer, and we'll get to this later. I'm not going to talk about it too much now. But it's this kind of data that, to me, is the selling point for robotic precursor missions. It's having that perspective that you can't get from satellite images. And this famous, well, if you've read some of Richard Grieve's papers on Mustaston, this famous Discovery Hill site. You can see some kind of, these trees are more or less than 10 meters. They're just a few isolated patches, but tundra is what most of Mustaston is like. And so this annotation here is annotation from the mission control team, who again had not visited this site before. So some questions that they're answering themselves. And again, we'll come back to kind of how useful this type of data was in a second. So in year 2011, we essentially conducted 2 separate sortie missions over 2 separate weeks, with then a week at each end for setting up and doing some more ground truthing. So in the first week, we had an astronaut with a robotic assistant, and this is something that I'll focus on a little bit here. And it's been discussed a lot. There's a lot of pros and cons, I think, for having a robotic assistant during a human sortie mission. And so that's something that we tested during week 1. Then in the second week, we really complicated things for ourselves. We essentially left part of the team and the robot at that first. So also these were conducted at 2 separate sites. So in the second week, part of the team with the robot was left at the first site. And that essentially was a post-cursor scenario where the robot, directed by mission control, continued collecting more data. And then we moved part of the team with the analog astronauts to a new site, and conducted activities there with some basic mobility in the form of all-terrain vehicles. And so that was kind of the scenario for the follow-up field season in 2011. During that second season, mission control, as you might expect, was divided into 3 main teams: tactical, science, and planning. This is, I think relatively straightforward for and consistent with other analog missions and actual missions when it comes to human missions. So tactical, the main comms with the astronauts, including a Capcom, providing instructions. Science was responsible, it's really a science background room carrying out processing and interpreting the data, and some communications with the astronauts, typically at the end of the day. And then planning, which essentially became a tactical process for the rover in week 2 as well. Just a quick recap. I'm not going to go through word for word. There were some instruments mounted or used as proxies on the robotic platform during that first week, and there's a list of them there. So essentially, pan imagery in the form of PanCam and LiDAR. We had the Raman, ground penetrating radar again, and then this C2SM is essentially a 3D panoramic kind of system. We then made various tools available to the astronaut. In terms of cameras, sampling instruments, we did have a handheld Raman and XRF, this kind of handheld stereo camera that created 3D models, and then tablets and PDAs for taking notes. I would say that, not on every EVA and not throughout every EVA were all of these tools used. We then tested this out too, with a decade later. I'd love to kind of essentially rerun this entire 2-year mission again. I think one of the things to look at again is the trade-off between having instruments in the hands of astronauts in the field versus having them in the habitat, say, where some more sample analysis can be done after each EVA. And again, pros and cons for both of these that I'll try and just touch on a little bit in the short time that I have. So one of the important things that we did between those 2 field seasons, they were both conducted at the end of August into September, primarily weather and bug driven up in that part of the world. And so we held 2 planning workshops separate for essentially, we considered these 2 weeks 2 separate missions to the 2 separate sites, one with and without the rover. We came up with 5 EVA traverses per site. I would say that we had in this scenario only 2 astronauts with so 5 traverses each. And the typical things that you would use in planning traverses, but of course most importantly here was having the robotic precursor data from the previous year. And so these were one of the things we looked at too, right, is how close or not the actual versus the planned traverses ended up being. So this is week 1 at the rim site. There was a landing site. This was actually some quite challenging topography for everybody, with some lakes and quite steep slopes. And then in week 2, this topographic high here, this is a contour map. This is Discovery Hill, and our landing site was over here in this relatively flat location. So, there's things that we had to take into account up in Labrador that we wouldn't have to on the moon in the form of lakes and water bodies, and that came into EVA planning. But, you could take these as rills and accessible craters and things. And I think, our approach would be fairly similar. Okay, so in week 1, again, we could have made this and we'd go back and look at doing this a variety of different ways again. But one of the things we were interested in doing, and a lot of this was due to our collaboration with Professor Tim Buff at the University of Toronto, who a decade ago was developing, essentially teach and repeat functionality for rovers, so that, once you've taught a path to a robot, it can then autonomously redrive that path without any human interaction. So it's a really powerful tool to have. So what we did in that first EVA was actually have the astronaut drive the rover, which took place relatively quickly. Only took about an hour to cover, quite a bit of ground. That path is then learned by the rover, and then essentially astronaut 1 returned to the lander and then conducted, the remainder of the EVA. During that time, they were never too far apart from each other, but the second astronaut was investigating geology proximal to the lander. That was obviously on the first EVA on day 1, and then we expanded from there. Again, I'm not actually going to focus too much. There's been, I think there's much better examples of analog missions out there with, real-time comms with astronauts, the whole Desert Rats series, where I think there's many more valuable lessons learned than we had because of the communications issues that we had. So again, I'm going to focus a little bit on some of the lessons learned from the use of robots. We did obtain analyses and samples, and we did look at in-field versus back in the habitat / the base camp type of scenario for analyzing samples. So in the second week, again, we split the team into two, and then essentially in the original location, this is the rim site, we had the robot that was, had learned a network of paths. It was able to return fairly quickly based on, some questions that had come up in the intervening, essentially a weekend, so not too much time, but a few days where the mission control team had looked at the data more, looked at the data collected by the astronauts. They had some new questions, and so we were able to send the robot back to some of the sites already visited, or sites sites along that network of paths. We also then, looked at expanding where we'd been with the astronauts into the new sites. Week 2 and the other side of the crater, we had this Discovery Hill site, and so this was astronauts only, 2 astronauts with all-terrain vehicles. Actually, if it's on the call, but some of you may recognize Raymond Francis, who's now down at NASA Jet Propulsion Lab, and is quite heavily involved in the Perseverance rover ops, of course. Again, 5 EVAs, and here, one of the priorities for this mission, like Moonrise and other missions planned for the moon, is sampling impact melt to further our chronological understanding of the moon, and in this case Mustaston. I do not expect you to read this, but we found kind of during that the first week, we really focused in on the second week and gave the astronauts, this wasn't the whole mission, but we wanted to look at creating some quite accurate hypotheses, not accurate, but a couple of hypotheses, and with some detailed things that they should look out for in the field, and so for each of the hypotheses, because it was actually unknown about a decade ago whether Discovery Hill was part of the so-called continuous or coherent impact melt sheet, or whether it was part of the ejecta deposits in the rim region, so analogous to a melt pond and a lunar crater. And we actually got some really neat science and really neat results out of this. So getting to lessons learned, value of robotic precursor data. I think it's clear from our understanding in these analog missions that having robotic precursor will just really maximize what you can do with humans in terms of return. You go into the field much better prepared. Even with the resolution that we have through NAC imagery on the moon, nothing is the same as having that perspective from the ground. And so this is a fairly good example. This is a quick bird image at 60 centimeters a pixel, so fairly analogous to what we have for the moon. And you can look at it at a perspective. You can see some, what is this? Is this stratigraphy? Is this layering? There's a brighter patch here that was nicknamed Fred. We'll come to that in a second. But, with LiDAR on the ground and in that panoramic image, and I'll show that again, quite clearly, I think most geologists, especially when you can zoom in and play around, you would interpret these as columnar joints. And this is an 80-meter thick cliff section of impact melt rock. It's actually one of the most spectacular outcrops in my mind on the planet in any impact crater. It was interpreted decades ago as an igneous sill, and you can kind of see why when you look at this kind of image. So in addition to that, you have range and scale information, and having this precursor data also helped in orientation and navigation actually during, after the astronauts landed. And this again is that panoramic perspective. The science team kind of went in, annotated this, provided a bunch of questions, so the astronauts had this when they went to explore this site for the first time. And I don't think I have it on the next slide. To cut a long story short, and we've actually published up the science of this, this is now interpreted as a melt pond. And so actually my kind of screen at the top is a Kaguya image of Tycho. So you've got this, terraced rim region around many complex or all complex craters on the moon. And so we interpret this melt at Mustaston as being a pond in the terraced crater rim region. And that actually came out of, some of the data collected in this analog mission. So just to kind of summarize, these are incredibly useful products. It really helps when you're looking at steeply inclined topography that, really doesn't show up as well in a top-down look. Provides, just that, I still like going up to topographic highs and getting a big overview of the landscape when I'm doing field work, and it really gives you that perspective before you go there. One addition, LiDAR is really useful, but multispectral, of course, if you could have some compositional data too, you could have even more information, but I think, just basic imagery combined with LiDAR from a precursor mission, and it would be a long way ahead without having that. Just quickly on LiDAR too, this is something that I've been a big fan of, again, for many decades. And this is the kind of reason. You're in regions, this one is actually now from the Horton crater in the Canadian Arctic. It's fantastic where you have shadows that you can't see into with regular imagery. So, it's good for, and the intensity data returned from LiDAR 2 helped us pick out zones of alteration here, not appropriate for the moon, but still interesting. And, you really see features in quite fine scale layering in this LiDAR data that you really can't pick out, or it's difficult to pick out here. LiDAR is also good in these kinds of environments. You haven't worked in these kind of true desert environments in various parts of the world. It's really hard to judge scale and to figure out where you are. And I know the astronauts, the Apollo astronauts really talked about this being a challenge. I always like showing this too. This is something that we didn't have LiDAR for, but we wish we did. How big is that rock, right? I'm a rock climber, and it looks like quite a nice little boulder problem, maybe even a bit too steep for being a boulder. You can see tents in the background, but that's still difficult to judge this. But when I put mark here for scale, this is a pretty teeny little rock. But I know when I first looked at this, I was expecting this big cliff face. And so just having visible imagery is really difficult to do that, so that again is another strong case for LiDAR. In particular, again, where you have this very kind of, bright scenario on the moon, where, it's really hard to judge, how far away is this ridge without something like LiDAR. So take a LiDAR. Okay, I can see I'm kind of going to run a little short on time, so I'll try and go through some of these slides fairly quickly. So looking at instruments in the field, and again, I know that there's been a lot of work done, and more recent and more ongoing work, including through some of the SSERVI teams looking at this. It is a trade-off, and I don't think we have a good answer for the perfect balance of instrumentation and technology to give to the astronauts versus, in a habitat versus leaving for lab-based analyses on Earth. It is a useful little discrimination tool, but it does take time in the field. So you've essentially reduced the length in particular of an EVA traverse. So maybe that outweighs the use of these instruments in the field. The two astronauts did get a lot and make a lot of use of having these tools in the habitat. So, in an evening, they would collect some data on the samples that they collected, send that back to mission control. And that allowed them to do some iteration between the different traverses. At the end, we also did, provide a sample mass restriction. We kind of have that anyway going up to the Arctic. It's usually a cost and a volume one, getting all of these samples back in your twin otter. But this, this information was useful for triaging samples. So I think, overall, having the geochemical data in particular for X-ray fluorescence was very valuable. I don't think we have a good answer from at least our work there. And again, I know others are working on it as to, what the perfect balance is between astronaut hand, a rover for that matter, habitat versus Earth. Okay, so, quite again, an outstanding question, and I think there's a lot of strong opinions out there too, is, astronaut rover cooperation. You know, I think we can say from our this analog mission that having the addition of a robotic assistant does enhance the mission performance, but it definitely comes at a cost of astronaut EVA time. But if you think about the question is, it may, and I'll show you some stats in a second, you got to think about the mission as a whole. If astronaut plus rover actually increases the amount of return you get from a mission, even though it reduces the astronaut time spent not, worrying about the rover, then perhaps it's still, a positive thing to do. We do have some stats here, for example. I just pulled out, this one particular EVA. Actually, no, sorry, this is for the entire week. So 15 working minutes on EVA. So about 13% of the time was spent on robotic work, either driving the rover, like you see here with Raymond, kind of manually driving it out on this first path, or in other aspects related to the rover activities. But because of having that rover there, we essentially had an additional 546 minutes of robotic operations with more data collected from various instruments. And, a lot of, because this rover had a lot of autonomy, it really did free up the astronauts to do a lot more. And so, I think the balance, and this is something that I would like to revisit and do more work in the future before we go back. I think there is greater science return from having a robotic assistant. It does have to be very mobile, and it does need to have autonomy. Otherwise, that benefit may not be there. There are some precise benefits too. People have talked about using rovers for laying out seismic networks, astronomy experiments. Some precise work can be left for the rover to do, and potentially even hazardous tasks as well. Okay, the value of robotic precursor work. I don't think this is going to happen, but I would say we should be sending robotic precursors before any human mission to the same site. I know we're ramping up Artemis very quickly, and that might not be possible for the first couple of missions, but I really hope that we get to do this because, from this series of analog missions, it really does enhance the science return and the, essentially the execution of that sortie mission, especially when we're talking sortie missions of only a few days where the astronauts don't have much time on the ground. And so, definitely extends the duration of a mission. Sorry, I should be talking about post-cursor work here. I'll get to precursor, but I would say the same thing for post-cursor work that is shown on this screen. If you're going to have a rover there for precursor, of course, it makes sense to use it during and then after. I know Jack Schmidt's talked about this. He would love to have, had a rover there, potentially for months and years, right? You could imagine, a scenario where the rover is able to work for several months at least. And as scientists back here on Earth are analyzing samples, going through materials, they come up with new questions, new hypotheses. Wouldn't it have been great if we'd gone to this outcrop or taken that sample? And so I think this is very important. And, even a decade ago, we kind of had this technology, and we definitely have it now. This is a lot of technology being transferred to self-driving cars and things these days. But once, a robot has learned a network of paths, you literally need to hit go, and, it can drive 5 kilometers on its own and get back to one of the locations that you previously visited. Probably much faster and more accurate than us, right? As humans, it knows exactly where it was, where it went, and what that particular rock was, whereas, a lot of things may look the same to the human eye. So definitely a huge value in having a robot left after the sortie missions. Okay, so I think I do have enough time to now talk quickly just about CanMoon. So for those of you who are at the most recent lunar surface scenarios workshops, this is something I talked about then. So I'm going to talk present some of that data again. This was a purely robotic lunar sample return scenario, which is also still talked about for the moon, because it does open up a lot more of the lunar surface than we can just get humans to. This again was a collaboration funded by the Canadian Space Agency and primarily a partnership between Western and the University of Winnipeg. So like our previous analog missions, and in fact, with a decade of experience under our belts, we went in with even more detailed scientific and operational objectives. So I'll let you read these, but the 4 science objectives here. One of the most interesting ones was looking for mantle xenoliths in a landing site region, looking for volatile rocks, and of course, collecting the best samples to bring back for dating. And, how you go about doing that is a big question. Probably more important here and more of interest for some of you is the operational objectives. And one of the things that we wanted to do, probably one of the more unique things, was using VR, but looking at this operation structure to conduct 24/7 real-time lunar surface operations. So this was kind of 2 years after our Mars sample return missions, which of course is not run with 24/7 mission operations, whereas this was something that we wanted to look at here. So as with the previous missions we've done, we started with a clean slate. We tried to encourage everyone participating to not Google, geology of Lanzarote. And in fact, they didn't actually know exactly which island they'd be going to, and the Canary Islands initially. But this is Lanzarote, one of the bigger islands in the Canary Islands. This was chosen initially because the CSA and ESA were going to do some follow-up activities. Those of you familiar with Pangaea, ESA's kind of astronaut training program, that's in this kind of these recent volcanics that we also targeted here as well. So again, but we started with a blank slate, conducted a lot of site selection, conducted regional maps, and then went in and planned a series of EVAs. So in terms of the mission operation structure, for Can Moon, without humans in the loop, we still actually kept a tactical team, and we call this an interpretation team, led with an overall science lead. Tactical science, as you can imagine, consisted of the instrument leads. This is where GIS and localization was included. One of the things that we also wanted to look at was autonomy. Those of you familiar with Curiosity and especially Perseverance, JPL's Aegis software provides some level of autonomy, particularly for the ChemCam and SuperCam instruments. Do we need is that kind of autonomy useful for lunar missions where we do have the ability for almost real-time communications? So that's something else that we looked at too. We then had the science interpretation team that was working independently but in the same room. One of the highlights from this was the importance of this interpretation manager to act as a liaison between the 2 parts of the science team and the planning team. So planning obviously had all the uplinks and downlinks, as well as long-term planner, et cetera, et cetera. I know most, analog missions, simulated missions are doing this too, but if you didn't see it on the previous slide, we had embedded documentarians, so really keeping incredibly detailed notes of everything that was going on, so that we could look back after the fact, when key decisions were made and, determine why, and obviously get into if whether those are the right decisions or not. So we did want to look at shift work. This is something I've been thinking about, and is actually quite a good rationale for doing high Arctic analog missions as we ramp up for Artemis, because in the summer in the high Arctic we could do actually a true 24/7 scenario without having to have floodlights out. In Lanzarote we just had essentially 2 of the 3 shifts that you would have. We did have a hardcore set of students, so we had a shift that ran from 3:45 a.m. Eastern. Actually doing this, with hindsight in Lanzarote worked out well because they're 3-4 hours ahead. So, they would be starting there in the morning. We'd start even earlier, run shift 1 and then shift 2 with a half-hour overlap. And one of the things we explored that, we're still in the process of writing up from this one is, how big of an overlap? There's trade-offs. You could obviously sit down both teams for a couple of hours, but that's not realistic or a good use of people's time. There's 50 minutes too little, half an hour. So we kind of looked at that and then looked at kind of 2 well, because of how we designed it, we had to look at two different shift handovers. Shift A to B was done in person with documents, but that kind of overnight shift B to A was done with documents only. And we looked at the pros and cons of just doing that. Just quickly, this is the type of terrain, beautiful fresh volcanics. These are from the 1800s, so these are really recent lava flows in this part of Lanzarote. Very little vegetation, although, one of the interesting things about Lanzarote is that lichen's protected, and so we actually had to do quite a few workarounds so that we didn't drive or walk over any lichen in the field. That's over quite a lot of these areas. But this kind of data set, and the science team was successful. We have analyzed these since, but hopefully those of you with keen eyes, will look at this data and be able to spot, olivine in these, what are definitely mantelazine. So, mission success. Okay, and again, I did apologize for those of you who were in the lunar surface scenario workshop, because I did quickly run through these lessons learned. And this is something that I know the Basalt team and blanking on old Finesse looked at a bit, but what's the ideal layout even for a mission control, right? We're kind of used to rows looking at monitors in mission control today down at JSC, but is that, the ideal scenario? So we looked at, and we had an open concept room that we were able to maneuver around, throughout the week. And the team did like this open concept. It allowed for better, easier communications and even physical movement around a series of tables, essentially. So kind of pod type of structure. We did have physical separation between the planning and science teams. That had its benefits in terms of, the two teams being able to work without distraction and, everything going on. But it did present some challenges for clear and efficient communication. And so we had these science and planning integrator roles that we kind of thought about beforehand, but they really became absolutely critical. And we actually developed their roles throughout the 2 weeks of this analog mission. And, benefits there, working back and forth, getting vital information on traverse timing. The planning team might be discussing how many, analyses could be done, and that science integrator could, give real-time answers. And it really helped to give adjustments to the long-term planning too. Back to the shifts, we do have some metrics that we're, I guess, still pulling together. We're writing up a paper on this. I'd say overall, as you may expect, but we have the numbers to show that the in-person shift handovers were slightly more efficient, and that that team that you hand over to was better briefed, but both actually did function quite well. And we really augmented and again developed throughout these 2 weeks of the documents that were provided to that second shift, because there's some friction, right? You're coming in and you're literally sitting down in the same seat as the previous person, and you may want to take the mission in a slightly different direction, and so there's a back and forth to be watched. So the really detailed handover documents were definitely critical to have. Again, rich and annotated figures. Picture speaks 1,000 words. So we're definitely the most effective. We ran into this, which is why I know I was excited at that last workshop to see so much work being put in by various groups, JSC, Goddard, MIT, on, better data visualization and management software. And so we didn't have that fully in place, but I do know that groups are working on it, and it is absolutely critical for seamless integration and interrogation of different data sets. We did look, we could have made this an entire kind of analog mission on its own, but just, from the little work we did on using VR, again, may come as no surprise to some of you, that did enhance the situational awareness for the mission. We did actually cause some jealousy in the mission control team, because we did have different groups using VR and not. And so, but we did, because of that, get some, fairly good quantitative results on how useful VR was. Okay, I think this is my last slide. I think there is still a role for automated data analysis. It's a different kind of rationale than we have for Mars. A lot of the rationale for Mars is bandwidth. It's the time delay, between getting data down to Earth and, having to look through that, interpret it, and then, sending up commands to the rover. Here, it's actually a bit of a way to help automate the science interpretation and processing when you're doing, full-on ops for 24/7 for 14 Earth days. Having some automation there definitely did help. And we've got some neat work that one of our PhD students is working out, for example, on spotting mantle xenoliths in the basalt. They actually, were able to pick it up more than the human mission control team was. And with that, I'll just close and quick look forward, and a bit of a shout out for the need for more analog studies in general. Again, I think I'm probably preaching to the converted. In particular, I think more work done in impact crater analog sites. We have lots in Canada, so I welcome collaboration. There are many more than the Mustaston crater that I showed. Just for kind of up close scale, it's a picture of me with a lot less gray hair here about a decade ago. Just spectacular rocks, these columnar jointed impact melt rocks that, we all over the lunar surface. This is the West Clearwater Lake structure in northern Quebec, where we took the NASA SSERVI Finesse team a few years ago now. This is an immense structure. Nobody had visited it in the field since the 1970s when we went there in 2014, and there's so much work to be done there. So you can do these really science-driven analog missions at sites like this. Not the best site for sending astronauts or rovers to this particular series of outcrops, but so much material and untapped resources to go to. And I think with that, I'll stop sharing my screen so I can see everybody again. And we can go from there. Or maybe I'll leave the slides for now in case anybody wants me to go back. But over to you, Jen.
Yeah, great. That was fantastic, Oz. I'm having whiplash because there was so much great content in there. So we do have a few minutes for questions. If folks would like to ask questions, you can put them in the chat and I'll try and monitor that. You can also raise your hand. If you mouse over your name in the participants window, you should see a little hand pop up. And if you click that, you should raise your hand and I'll try and call on folks. So while people gather their thoughts, I do have a couple of questions, Oz, just to start. So one is on the topic of field instruments. So it's fantastic. There's been so much work done on using, field portable handheld instruments and the value of those, and then the drawbacks, right? There's pros and cons. So we could have a whole seminar about that. The one thing I wanted to ask you about was the LiDAR. So I have developed an appreciation of LiDAR for the past, half a decade or so, using it in the field in Idaho at craters of the moon and in lava tubes and over these complex volcanic terrains. And just like you said, it's the situational awareness, it's the fidelity of the data. You can go back into the lab and make measurements. It's the increased exploration utility for traverse planning and looking at operations further out. So I'm wondering, how do we take the LiDAR instruments in the field and move those into flight-ready units, right? Because LiDAR is usually high power. And so in general, your thoughts on moving from field instruments to flight?
Well, it just so happens that the integrated vision system that you mentioned at the beginning has started down that line. So LiDAR historically, at least in Canada, had been thought of just for kind of rover navigation purposes. And back probably 15 years ago, the Canadian Space Agency had kind of identified LiDAR for that fact. But starting a decade or so ago, and like you say, more recently, LiDAR has become an amazing scientific instrument too. Canada does have some experience flying LiDARs, not rover mounted or handheld, but on OLA, the OLA instrument on OSIRIS-REx. And this integrated vision system, what we're trying to do is actually partly comes out for the motivation and the results of Mustaston. It's taking a visible imager, multispectral and LiDAR, and actually a multispectral LiDAR, and putting that into one sensor package. And so we are working on the development of such a system. We'd love to talk to folks about taking that further and getting it flying. you're right in that it is relatively high power and high mass, but we're still looking at an instrument that will be getting down to about 10 kilos, and so it's not feasible. We're looking at micro rover types of scenarios right now in Canada. It's not feasible for that, but any kind of regular size rover and an astronaut size of platform, then to me it's totally feasible. And again, the technology is coming a long way, such that power I don't think will be as big an issue as it was. But yeah, I'm a big proponent, like you are, for LiDAR.
Great, thank you. We have a couple of hands up. Laura Kerber, if you want to unmute and ask Oz your question.
Hi, this is Laura Kerber from JPL. I was very interested in your team structure and how you had all your backup teams and everything, and I was just wondering who held your decision authority. So you'd have the planners and then the tactical people, and who was ultimately making the decision about what the astronaut should do next?
Okay, so this is going back to the original one. I'm actually, it was interesting going back through all of the files and things putting together this presentation, because that one happened a decade ago. But I'm pretty sure we put the authority with the Capcom and the tactical team back for that. The astronauts did have some discussion, and we did have there were times when we gave the astronauts some autonomy as well, and so they could question certain types of commands or come back with some back and forth. So I'm not sure that was a great answer to your question, but I can definitely dig into our kind of archives to get back to that one.
Yeah, because I'm sure with small enough a team, you can probably come to a consensus also and not just have one person making decisions, but very interesting. Thanks.
Yeah, for sure. Yeah, so our science back room is quite, maybe about a dozen people though. So we did, try and have consensus before we started discussing that with the astronauts, for sure.
Great, thanks. We have a question in the chat from Rob Mueller. Did the rover use GPS? How did it navigate?
So actually, part of a separate study that Tim was working on was not using GPS. GPS was only there for ground truthing. So it was using, basically just visual recognition. It was using a stereo camera and actually a LiDAR back then to, basically collect that data, recognize features, and then match that up when it's driving. I'm forgetting on the technical term for that, but GPS was not used for the rover navigation.
All right, great, thanks. We have a couple more hands up. Ernie Bell, go ahead.
Hi, thanks. So yeah, it's Ernie Bell with UMD, just finishing up a PhD there. One thing I wanted to point out is that with your second study there with the mission control information, that you're looking at the mission control structure. I think that's really awesome that you were doing that, both with shift handover perspective. And I think you highlighted one thing there that beyond just the shift handover, but just that the structure that's going to be needed and the discipline, and therefore that feeds into the training that the mission control team will need for these types of missions, which is a really key part of these types of things, which oftentimes the field is what gets focused on. So I think that's excellent that there's some work being done on that. And then I actually have a couple questions on the first section there. Regarding the EVAs, the one conclusion you had was that they take a lot of time when they're when you're using rovers along with it. A lot of the time ends up being with the associated with the rover, or at least a significant percentage. Was that simply because of the OPSCON that was used, though, with the crew member who was EVA having to guide the rover on their initial learning traverse? And then I have a second question, too, to follow up.
Yeah, that was definitely part of it. So, if you had, better infrastructure, better comms, you could argue that, it would have taken longer, but we could have had, mission control teleoperating the rover. So that would reduce that a bit. But there were, some experiments, some instrumentation on the rover that the astronauts used to collect some data too. So, yeah, and if you'd actually had a robotic precursor in place, let's say for months on the moon, you could have, explored a lot of that terrain already with a rover, and so to avoid some of that. I think we probably have it in the stats somewhere as to how much of that 13% of the time was spent driving the rover. And so I can probably dig that out. You know, if I had to guess, maybe about half that time was spent driving, and the other half I think they still would have done, you know, using the robot for taking various measurements.
Yeah, okay, that makes sense. And then regarding the EVA traverses, I know you had the traverse itself planned out, but how much of the individual task along along the traverse was pre-planned and timed so that you expected to execute, say, within 6 hours or something like this, and you expect to hit science stations A, B, C, and D, et cetera, and do task X, Y, Z at various locations versus just we're exploring the area and we're trying to get data for these types of instruments?
We did have it fairly structured, you know, kind of Apollo-like, back in these missions about a decade ago. So yeah, they were, you know, there was a number of stops, and one of the things we wanted to look at, you know, was, you know, how efficient and how well that was executed by the astronauts. And so yeah, but there was a number of stops and some tasks, and so we do have all of the time information from those EVAs too.
Okay, great, excellent, thank you.
Great, thanks, Ernie. And Gareth Morgan, you want to go ahead?
Oh yeah, thanks. Hey, Oz, it's Gareth from
Hey, Gareth.
PHI. Hey, how you doing? Just quick science questions. Apologies if I missed this in your talk, but how were you able to determine that melt was a ponded melt rather than part of the coherent melt sheet?
I can. How about I send you a paper afterwards?
All right, that sounds great.
But essentially, it comes down to what is underlying it. There was this one outcrop that was kind of highlighted. I probably don't have time to flip back to the slide, but we were able to ascertain that there's some impact breccias beneath this beautiful columnar joint that you're seeing there, that we were able to determine was consistent with ballistic ejecta. And so that, you know, puts it outside the transient cavity where you expect the main body of that coherent melt sheet to be. And then it was some regional kind of mapping where, again, essentially this discovery hill is like, it's a wedge shaped. And there's some, you know, evidence for a fault structure running, you know, concentrically to the rim of the Mustaston crater. Those are probably the two main lines of evidence, but my PhD student, Marianne Maida, did kind of write that up in more fully into a pure science paper in meteoritics and planetary science that I can share.
Yeah, that'd be great. Thanks very much.
Great, well, thanks, everyone. We're almost at the top of the hour, so I will take the chair's prerogative and ask the last question. So Oz, since you've shown us all these great field sites in Canada, if folks are intrigued and wanted to do field work in Canada, what's the process? What do people do?
You know, it depends on where these sites are. You know, obviously they can feel free to reach out to me. You know, I'll happy to collaborate or just give you some guidance on how to get to some of these sites. You know, most of these really, you know, good high fidelity analog sites are pretty remote. You know, the West Clearwater Lake, Mustaston, Horton, and the high Arctic. So having some knowledge on the ground is definitely important. You can, in theory, do all of this off your own back and charter, you know, private companies to get you there. We do have a program called the Polar Continental Shelf Program that kind of does what NSF does for Antarctica and providing that logistical support. And so, you know, going through them is definitely what I'd recommend. You can do it as a Canadian and I get in-kind support. You can actually do it on a cost recovery basis as an American PI as well. So yeah, every site is different. Mustaston, we actually did all ourselves. You can actually fly commercial to Goose Bay in Newfoundland, and then it's about a 2.5 hour twin otter flight in. So yeah, every site's different. I can give you a bit of a rundown if you like, but I just don't hesitate to reach out.
Fantastic. Well, thank you very much. We're at the top of the hour, so I'm going to respect people's time and let everyone jump probably to their next online meeting. So thanks again, Oz. Really appreciate it, and we'll see everyone at the next meeting.
Sounds good.
Thanks,
And,
everyone, for joining.
I think probably some of us at the analogs workshop in between.
That's right.
All right. Thanks, everyone.
Thanks, everybody.